Okay, picture this for a second. Think about the incredible forces involved when huge pieces of metal get fused together, like the intense heat, blinding light, turning solid steel basically into rivers of molten metal. And then it cools down, often super fast, right? In seconds sometimes. Welding itself is amazing, no doubt. It creates these incredibly strong bonds, holding up skyscrapers, bridges, massive pipelines. But, and here's the thing, that intense process, it leaves stuff behind. A hidden legacy, you could say. Invisible stresses locked inside in the metal, tiny changes to its structure, and sometimes you get these areas near the weld that become really hard, even brittle, almost like tiny, unseen cracks waiting to happen, even in a weld that looks perfect. So today we're doing a deep dive into something I find fascinating. It's like the secret art of undoing some of those less desirable side effects of welding. It's a pretty sophisticated process called Post-Weld Heat Treatment, or PWHT, as you'll hear it called. And believe me, it's way more involved than just, heating something up.
That's absolutely right. Yeah, our mission today is really to unpack what PWHT actually is. And crucially, why it's not just a nice to have, but often absolutely vital for the safety and the long-term life of pretty much any significant welded structure. We'll also walk you through the science, the nitty-gritty of how it's done, because like you said, it's not just about brute strength. It's about making the structure resilient, reliable, smarter, really, for the job it needs to do, potentially for decades.
Okay, let's dig into that then. At its most basic, you said PWHT is a heat treatment done after the welding's finished. But if the weld looks good, it's holding everything together. Why the extra step? Why this complicated heating process afterwards? What's it actually fixing?
It's a great question, and it gets to the heart of it. See, while welding creates that strong physical connection, the incredibly rapid heating and the equally rapid cooling, well, it creates a whole mess of internal microscopic issues. Think of it maybe like the tiny invisible springs coiled up really tight inside the metal. Welding creates these residual stresses. They're locked-in forces. And if you just leave them there, they can genuinely be like a ticking time bomb. That's the main thing PWHT tackles. Because those stresses can lead to failures, cracks appearing later on, even under just normal everyday loads.
Okay. So it's dealing with invisible problems left by the welding itself.
Exactly. And beyond the stress, there's the heat effect. The extreme temperature of the arc creates very hard, sometimes brittle zones right next door to the weld. We call that the heat-affected zone, or HAZ. PWHT essentially softens those hard spots, makes the whole area more uniform in its properties, less likely to just snap. There's also a less common but important case where you might actually normalize a joint with heat treatment to specifically restore toughness in that HAZ. But you have to be careful there. That specific treatment can really knock down the strength of the weld metal itself. So the filler metals, the welding consumables, they have to be chosen very, very carefully right from the start if you plan to do that.
Right, so it sounds like PWHT isn't just about the weld bead itself, but the whole assembly, the weld, the metal next to it, making sure everything is, well, stable and ready for whatever its job is. So what are the real-world upsides? What does it actually do for the structure when you manage these stresses and control that hardness properly?
Well, the benefits are huge, honestly, and they tie directly into safety and how long something lasts. When you effectively reduce those residual stresses and temper that HAZ, you dramatically improve the joint's resistance to brittle fracture.
And that's critical, I imagine. You don't want things just snapping.
Absolutely not. Think bridges, pressure vessels. Sudden failure is catastrophic. PWHT massively reduces that risk. It also significantly improves resistance to something called stress corrosion cracking, or SCC. That's a major problem in tough environments. Pipelines carrying corrosive stuff, for example. SCC loves stress, so reducing stress helps fight it.
Okay, so better resistance to breaking and corrosion. Anything else?
Yes, something very practical too. By relieving those internal stresses, you allow the welded parts to be machined to much tighter, more accurate dimensions. If you've got internal stresses pulling and pushing, the part might distort when you try to machine it precisely. PWHT stabilizes it, essential for parts that need perfect fits.
Which is why people often just call it stress relief, right?
Exactly. That's the most common term, because reducing residual stress is usually the primary goal. And the way it works is pretty neat, actually. At those high PWHT temperatures, the steel's yield strength, its resistance to bending or stretching permanently gets much lower, becomes more pliable, let's say. This allows the atoms in the steel structure to kind of shift around, rearrange themselves just enough to release those locked-in stresses. It's like a muscle finally unknotting.
Okay, that makes sense. But you mentioned this is sophisticated. It's not just chucking it in an oven, right? I'm guessing the how involves some very precise control. What are the key things engineers need to manage? The dials they need to set, the timing they need to follow?
Oh, absolutely. Precision is everything. You're talking about a very carefully controlled thermal cycle. Specific codes and standards dictate exactly how it needs to be done. There are basically 4 critical parameters.
4 key things. Okay, what's the first one?
First up is the maximum heating rate. You can't heat it up too quickly. Why? Because you want to avoid large temperature differences within the part itself. We call these thermal gradients. If one part gets way hotter than another part too fast, the expansion differences can cause the whole thing to warp or even crack. It's like pouring boiling water into a cold glass sometimes.
Right, thermal shock, basically.
Exactly.
Yeah.
And this control is especially crucial above around 300 degrees Celsius, maybe 575 Fahrenheit. That's where steel starts to lose a significant chunk of its strength, making it much more prone to distortion if stressed by uneven heating.
So how do they track that?
With thermocouples, little temperature sensors attached to the surface, placed strategically to represent the thickest and thinnest parts of the item. For typical carbon steels, you're looking at maybe 60 to 200 degrees C per hour heating rate. Depends on the thickness. Slow and steady.
Okay, slow heating. What's next? Parameter 2.
That's the soak temperature range. This is the actual temperature you hold the part at for the stress relief or tempering to happen effectively. And it's not one size fits all. It depends very specifically on the type of steel. Your standard carbon and carbon manganese steels might need around 600 C, that's about 1100 F. But for the tougher, low alloy steels like chromoly steels used in high temp, high pressure stuff like power plants or refineries, they need higher temperatures, often up around 700 to 760 C. That's like 1300 to 1400 F.
And getting that temperature right is critical, I assume.
Absolutely critical. It's what's known as an essential variable in the welding procedure qualification, the WPQR. That's the certified recipe for the weld. If you don't control that soak temperature correctly within the specified range, you might invalidate the entire procedure. You might have to requalify it, retest everything. Or worse, the part itself might be deemed unfit for service. Huge implications.
Wow, okay, so essential variable. Got it. What's number 3?
Number 3 is the minimum time at soak temperature, also called the soak time or hold time. The idea here is pretty simple. You need to make sure the entire thickness of the weld joint reaches that target soak temperature and stays there long enough for the magic to happen. Heat takes time to travel through metal, so the thickest section of the entire welded item dictates how long that minimum soak time needs to be. You need to guarantee temperature equalization right through the core.
Makes sense. Is there a rule of thumb for that?
A very common specification is 1 hour of soak time for every 25 millimeters. That's about 1 inch of material thickness, governed by the thickest part being treated.
Okay, 1 hour per inch. And the last parameter, number 4.
That's the maximum cooling rate. Just like you need to control the heating, you need to control the cooling afterwards, and for exactly the same reason. Cool down too fast, and again, you risk creating those damaging thermal gradients, leading to distortion or even cracking as different parts shrink at different rates.
So slow cooling too, down to what temperature?
Usually the codes specify controlled cooling down to about 300 degrees Celsius or 575 F. Again, below that temperature, the steel has regained enough strength and toughness that it's much less susceptible to damage from temperature differences. So often, once it's below that 300 C mark, you just take it out of the furnace or turn off the local heaters and let it cool naturally in the air.
Okay, heating rate, soak temp, soak time, cooling rate, all precisely controlled. It really highlights how critical that precision is for getting the benefits you talked about. But how does this actually happen in the real world? You mentioned furnaces, but also maybe local heating. How do they apply this heat treatment to, say, a massive pipeline versus a smaller component?
Right, good question.
Yeah.
There are really 2 main ways it's applied, depending on the job. You've got global PWHT. This is where the entire component or a very large section of it is placed inside a furnace. These can be huge, often fired by gas or oil. Couple of key warnings here, though. You absolutely cannot have the burner flames directly hitting the metal part. That creates intense local hotspots, exactly the kind of thermal gradient you're trying to avoid.
Right, you want even heating.
Exactly. And also, you need to make sure the fuel itself is clean. Specifically with oil-fired furnaces, you don't want impurities like high sulfur content, which can actually be detrimental to some steels over time.
Okay, so furnaces for big stuff. What about the other way, but local?
Yes, local PWHT. This is used when you only need to treat a specific area, usually a weld joint, on a much larger structure. Think of individual welds on a long pipeline, or maybe nozzles welded onto a big pressure vessel. You can't realistically put the whole thing in a furnace. For local PWHT, the procedures need to specify even more detail, not just the time and temperature cycle, but also things like the exact width of the heated band around the weld. That's the zone that must reach the full soak temperature. And they also specify the width of the temperature decay band, the area next to the heated band, where the temperature needs to gradually and controllably drop off down to that 300 C mark or so.
So you control the temperature profile across the CFIS, too.
Precisely. Other things become important, too, like exactly where you place the thermocouples within those heated and decay bands to monitor it accurately, and how you support the pipe or structure during the treatment. Remember, the steel is weaker at high temperatures, so you need proper support to prevent sagging or distortion while still allowing for thermal expansion and contraction.
And how do they actually do the local heating?
Several ways. Very common are insulated electrical resistance heaters. They look like flexible ceramic pads or blankets with heating elements inside. You wrap them around the pipe weld. They offer good control. You can also use gas-fired radiant heaters, sometimes shaped to fit around the pipe. And for some applications, high-frequency induction heating is used. That can heat things up very quickly and precisely in a narrow band.
Pros and cons to each, I guess.
Yeah, exactly. Gas furnaces can be portable and uniform, but size limited. Electric blankets offer great control, but elements can burn out. Induction is fast and precise, but the equipment is expensive and less portable. Depends on the job.
That is an incredible amount of detail to manage, whether it's a giant furnace or just wrapping a heating blanket around a pipe weld. So who's making sure all this happens correctly? Who's the person on the ground checking the temperatures, the timings, the equipment? How do you guarantee that precision actually happens every time?
That's where the inspector comes in. Their role is absolutely crucial. They're essentially the quality control, the guardian of the process. Their job is to verify a few key things. First, that the equipment being used, the furnace, the heating elements, the controllers, the recorders, is actually what's specified in the approved procedure. And critically, that all the temperature monitoring and control equipment is in good working order and, really importantly, has been recently calibrated. You need to trust those temperature readings.
Makes sense. Garbage in, garbage out if the sensors are wrong.
Precisely. Then, they ensure the procedure itself is being followed exactly. Are they using the right method? Are the heating and cooling rates within the limits? Is the soak temperature correct? Is the soak time long enough? Are they measuring temperature correctly? And finally, they're responsible for making sure all the documentation is done properly. Charts, records, everything needs to be documented to prove the heat treatment was performed correctly according to the code or standard. It provides that traceable record.
So it's a really hands-on oversight role.
Very much so. And just to sort of summarize the keys to effective heat treatment generally, you need adequate support for the part, especially when it's hot and weaker. You need strict control over those heating and cooling rates. You need that sufficient soak time for the whole thickness. Avoid direct flame impingement. Sometimes you even need to control the furnace atmosphere to prevent excessive scaling on the steel. It's a whole package of careful control.
It's really quite something. We've gone from the raw power of welding to this incredibly meticulous, almost delicate science of heat treatment afterwards. It really brings home how PWHT takes what looks like a solid weld and transforms it into something truly resilient, much safer, and dimensionally stable for its intended job. It's optimizing it, really, preventing those hidden issues.
That's a perfect way to put it. Welding joins things together powerfully. But PWHT refines that joint. It meticulously reduces the hidden risks, those stresses, the brittle zones. It ensures the structural integrity is really there, unlocking the full potential so these engineered structures can safely handle whatever demands are placed on them, often for a very long time.
So maybe next time you're out and about, think about the complex structures all around us. You know, the bridges you cross, the buildings you're in, the pipelines hidden underground carrying essential resources. What other hidden processes, a bit like PWHT, do you think are quietly working behind the scenes? Things we never even consider, but that are absolutely vital to keeping everything strong, safe, and reliable. Does knowing about critical steps like this, ones that are completely invisible to most of us, change how you perceive the everyday objects and the vital infrastructure that really define our modern world? Something to think about.